All right, guys, so in this lesson, we're going to quickly go over how to evaluate limits analytically. We did graphically and numerically earlier. Today, we're going to look at analytically. So with your basic limits, if you have the limit of a constant, so like in that first example, the limit of b as x approaches c is just whatever that constant is, okay? And I just noticed mine did not print over, so let me fix that. Okay, so the equals and the dot for the, and the I didn't print out. So if you've got the limit of x as x approaches c is just c, and then the limit of x to the n power as x approaches c is c to the n power. So essentially, y'all, what that's saying is it's saying that normally in good, nice functions, you can just use what we call direct substitution, okay? So, for example, if you've got the limit as x approaches 3 of 5, in this case, 5 is just a constant, so it is what it is. 5's never changing, no matter where you're approaching, whether you're approaching 3, whether you're approaching -8, whatever number you're approaching, it's just going to be whatever that constant is. In letter B there, the limit as x approaches 2 of 4x squared plus 3. So this appears to be a nice function. So we're going to attempt to use direct substitution. So to use direct substitution, it's what it sounds like. You replace the x with whatever you want x to approach, okay? In this case, it is 2, so then you would do 4 times 2 squared, and then add 3, and so that limit value would equal 19, okay? So when it's nice and easy, direct substitution, and you can simplify it based on whatever you would get when you plug it in. So it's basically a plug and chug. Sometimes things are nice, and it works out to where you can use direct substitution. Sometimes they are not, okay? So if we look down there at letter C, again, if you are letting x approach 1, if we use our direct substitution, you would end up having 1 squared plus 1 plus 4, and then divide that by 1 plus 1. And then whenever you simplify that down, your numerator gives you 6, your denominator gives you 2, which is 3. So that means that limit of that function as x approaches 1 would be 3, okay? Over to the right side of your paper, you see some properties of limits. So if you know that the limit of f of x as x approaches c is L, and the limit of g of x as x approaches c is k, if you have a multiple in there, so some number that's being multiplied to f of x, you can essentially pull that number out, and it's just whatever your limit is times that number. If they're adding or subtracting, you can simply take the limit of each one and then add or subtract them. Same thing when it comes to multiplication. So 2 limits are multiplied. You can take each limit individually and then multiply their numbers. With your quotients, it works as well, and then also with powers outside. So you can evaluate those limits and then do whatever the operation may be, whether it's adding, subtracting, multiplying, dividing. Again, that the division would only work as long as k does not equal 0, because please remember you cannot divide by 0. Okay? So that's just your easy, basic plug and chug. Sometimes you'll see limits that are involving a radical, okay? So in this example here, you've got the nth root, and again, some things didn't copy over when I made my PDF. You've got the nth root of x as x approaches c, and that is simply the nth root of c, or the nth root, yeah, the nth root of c. So again, plug and chug. So if you can use direct substitution, use it. It will be your friend. So in letter A, the limit as x approaches 8 of the cube root of x. You can simply attempt direct substitution. If it works, great. If it doesn't work, then you'll drop back and punt again, and we'll learn how to do that on Thursday. So the cube root of 8 is simply 2, so that limit would equal 2. In the second one, you've got the limit as x approaches 0 of the cube root of x. So again, cube root of 0, we're going to use that direct substitution. The cube root of 0 is 0, so that limit would equal 0. And last but not least, the limit as x approaches 0 for the square root of 0. Now this one's a little tricky, okay? So in this one, you've got to remember the definition of a limit, okay? The definition of a limit is that it converges to the same value, okay? Well, if we look at the square root graphically, okay, the square root graph starts at 0, and then it goes through 1, 1, and then through 2, 4, and 3, 9, okay? So from the right, this does converge down and the limit approaches 0, correct? Yes. But from the left, if we're coming in from the left, that does not exist. So because the left half of this does not exist, that limit itself does not exist. Okay, so remember that it has to be converging to the same value from both the left and the right. So since from the left side, so x approaches 0 from the left, is not possible, there's no graph back there, it does not exist, the entire limit does not exist. So that one is a tricky one that oftentimes students get confused, okay? All right, limit of composite functions. If you know the limit of g of x as x approaches c equals L, and the limit as x approaches L of f of x is going to be f of L, then what you can do is you can evaluate the inside limit and then plug that value into the outside. So essentially, you can, if you're doing the limit of f of g of x, then what you can do is you can do f of whatever that limit value is for g of x, and then do f of that limit. Okay, so it's kind of a double plug-in. We'll do some actual examples whenever you are in class with me on Thursday or Friday. We're going to spend quite a few days on this. I'm just giving you the basic overview for how you can evaluate limits using direct substitution. So I'm giving you the easy peasy ones. We'll do the more difficult ones in class later whenever I'm with you. So when you're talking about limits of transcendental functions and then also limits of trig functions, if you are following along in your Incredibles book, so this is going into page 47 if you have the binder, and then page, I think it's page 46 if you're in the spiral, but either way, you can find it in here in the 1.3 Evaluating Limits Analytically. So most trig functions are going to be nice where you can just simply plug them in and evaluate them. We reviewed trig functions earlier this year, so hopefully you're remembering how to evaluate trig functions. So use your direct substitution if you can. So the limit of tangent of x as x approaches pi, you're simply going to evaluate the tangent value of pi, and the tangent at pi is 0, which means that limit is going to approach 0, okay? So same thing with all of these. It's just you can use direct substitution to evaluate these. So if you do cosine squared of 0, well, cosine at 0 is 1, and 1 squared is 1. So that limit as x approaches 0 would be 1. You can have trig functions, like in option C, in example C, you can have trig functions in with exponential functions, so that e to the x. Again, you are simply just plugging and chugging. Direct substitution when it works. You'll see later when it doesn't work, but for these, it does work because anything to the 0 power is 1. Sine of 0 is 0, and so that ends up giving you 0 as your limit. Your natural logs, we do have to remember our natural log rules. So if you don't remember these rules, you might want to look back at some of them. So whenever you have the limit as x approaches e for the natural log of x squared, that would end up giving you the natural log of e and then raised to the second power. Well, the natural log and the e cancel each other out. It just goes to 1. And then if you remember your rules, the power of 2 comes down. And so the natural log of e squared is just going to end up being 2, okay? Same thing here whenever you have negative 1 squared and then e to the negative 1. So remember your negative exponent rules. Negative 1 squared is 1. If you have anything to a negative power, it drops down into the denominator. So that would be 1 over e. And although e is a decimal value, you can't tell me that exact value. It is some value. So it is approaching a value. If you had a graphing device or a calculator, you would be able to use it in order to tell me the actual decimal value that it would converge to. All right, last but not least, letter F, your cosecant of x as x approaches 5 pi over 6. Again, this is just a basic plug and chug. So if you have cosecant of 5 pi over x, you would find the cosecant value at 5 pi over 6. And that value there would be 2 because it would be 2 over 1, which is just 2. So that limit's value is 2, okay? So we will pick up with functions that are not nice in a plug and chug manner, meaning that when you plug in those values, your denominator would give you zeros, or it's an undefined value or does not exist value. So we will pick up next class with those.